Before I started my studies in AI and machine learning, I was very unsure what even research in these fields mean, because in my mind, I always thought that these people producing all this research, they were like super intelligent, that I could never do anything. So in hopes to maybe remove doubts in someone else, I thought I'll share my thesis presentation, which I recently gave on the thesis that I had. So without further ado, let's begin. Traditionally, search engines compared text with text. So if you have here a text query, your text query is compared in one way or another with different texts in the database itself. Even when searching through different modalities. So for instance, if you search on YouTube for a video, it compares the text of your text query to the text of the title of a video, for instance, or a description or something like that. This can be problematic because this can be very misleading sometimes. So what if we could directly search through multiple modalities without comparing the text itself? So imagine you don't even have any text, like a video without a title, and you wanted to search car engine sound. What if we can compare this text query with the audio of the video that we have here? So this is what my presentation and my thesis was about, where we looked for new novel ways to compare audio and text for retrieval. By the way, retrieval you can think of as just a different word for search. So in this presentation, I'm going to first talk about what this is all about, and then go through the baseline system. The baseline basically just means like the current best system in literature right now. Then we're going to compare this to our method that we thought of, which would be the novel part. And then lastly, the experiment and discussion. So in the experiment, I actually then tested it out, our method, to see how much better or worse it is than the baseline. And then the discussion where we go through basically, some future improvements, where it could have been wrong, what I would have done differently, or where it went well, and all of that. So let's start. Before this, a quick note, this thesis was also part of the DCase 2025 challenge, which is a machine learning challenge, and parts of which were a group effort. But the main novel system of this presentation was done by myself. However, special thanks to my team members, Giovanni and Fabian, and then also special thanks to Paul Primus, who helped us with the machine learning competition, and Shahnawaz, who was my thesis supervisor. So what is this all about? We want to search through audios via a text query. So we have here a text query, like I said, and then we compare it with the MP3 files of the text. Not quite MP3, we use WAV, but it's the same. To do this, we need to convert text and audio into meaningful vectors, then compare both. So basically, we compare the text into a meaningful vector. This is called an embedding. And then we compute the audio into a meaningful vector, which is an audio embedding. And then we just check for the similarity on how close both of these are. So some quick math recap. If you have here the X and Y axis, and you have here like one dot, this is one vector, and this is another vector, then the similarity will be very small. Let's say this is, the similarity will be very large. So let's say this is 90% or 0.9. And then if you have here instead 1 point, then this similarity will be very different. So this could be like this could be a similarity of 0.01. Something like that. So we basically just compare how similar these two vectors are to each other. The challenge, however, is to create meaningful embeddings for both modalities. How do you actually create these meaningful vectors out of something like text or audio? This is the difficult part. The entire system in general, how this would work then is the trained model is then used for retrieval. So how this works is we have here a model which is used on a data set. So here you have a large data set of audios, of like car engines, babies crying, I don't know, like sirens and dogs barking and all of that. And you compute the embeddings of the entire data set. And then when a user searches, the search is then converted into an embedding on the fly. Okay. And then this embedding is compared to every single vector from the audio embeddings that we have here. So audio 1 might have 11% similarity. Audio 2 might have 30% similarity. Audio 3, 45% similarity, and so on. And of course, we want to basically show the user then the audios with the highest similarity. And then we have here metrics. We have here recall at 1, 5, and 10, and then mean average precision at 10. You don't have to worry about this right now. This is just basically some statistical methods on how we can see how well the model performs or how bad it is. This is just important for the experiment part in the future, but for a user itself, it doesn't say that much. I mean, of course, the theory is that the higher these percentages are, then the better the search is. But at the end of the day, this is also just very relative to the person searching. So let's talk about the baseline system now. This is, again, the system that is currently the best one in literature. So the baseline system just fine-tunes transformer-based embedding models, okay? So transform is just like a type of architecture you can think of neural networks, and we basically fine-tune these embedding models that try to convert for instance, the word car engine into embeddings, and then also the same for the audio embeddings, okay? So let's say both of them are converted, and then the similarity is compared, and this should be similar. So if we have here the car engine and the corresponding audio, which we know 100% that this is a car engine sound because we have labeled it in our data set, we try to find the similarity. And of course, this should be very similar then, because we know exactly that this is the audio that we want here. But these embedding models are two different ones. So we check for the similarity. And if they are not similar, then we know that there is something wrong. And if they are similar, then everything is okay. So then the weights are updated, embedding models and the audio embedding models. This basically just is fine tuning, right? You just update the weights of a model to fine tune it. And yeah, the current baseline is trained on mainly three data sets, which is Clotho, audio caps, and wave caps. Clotho has the source freesounds.org, and it's clips of 15 to 30 seconds from everyday life, like dogs barking, car engines, people speaking, and all of that. And then each of sound has 5 crowdsourced captions. So those are humans that say like, oh yeah, this is a dog barking. And then we record that, and that is the Clotho data set. In total, there are 3,840 trained clips, and in total, that's, I don't know, some quick math, maybe 7,000, something like that. Audio caps instead which has as a source audio set, which is 10-second YouTube excerpts with human captions. So we have one video with it's like 10-second video with one caption. And of that, we have about 40,000 clips. Then wave caps is the largest one, which is web harvested audio and captions. And then the captions itself are refined by ChatGPT. And the composition is about 403,000 audio text pairs, which is a lot. That's over 7,568 hours of total audio. Actually, this audio data set is so large that it was actually even a bit larger than the entire training data that GPT-3 was trained on. So it's a huge, huge audio data set. And when I trained it, it took hours upon hours upon hours. I think it took like 3 days to train with that. And then we ultimately had to cancel because we didn't have any credits anymore. But yeah, it's a huge data set, and the baseline was trained with that too. The baseline system from last year was from our own in-house Paul Primus, and he used Roberta and Paz as the two audio and text embedding models. So Paz is the audio embedding model, and Roberta is a bird-style text embedding model. For the challenge itself, we tried a bunch of different embedding models too. So the first thing that we tried actually is just like, what if we changed the embedding models? And then we did a huge suite of different models to see how well they performed. So we had here, for instance, Whisper and GTRT5, or Data2Vec and BGE Base, and all of these different ones like Clap and all of that. I mean, here's just a couple. However, the baseline of last year was still better than all of them with every single metric. As you can see, the percentage here is a lot higher than any other model that we tried. And we tried 48 different combinations of all of them. And we also tried multi-layer projection instead. So just instead of projecting it with one layer, we had multiple layers to project it. And we got bad results too. The difference here is first it got like a lot better, but then it dropped after that. And even if we were to have stopped it early, the best early stopping still is worse than the baseline. So we didn't actually continue on that path too. But all of that is fine. And then we thought of a completely different system that we can try instead. And this brings us to our proposed architecture and the topic of this thesis, which is our method where we propose transforming the embeddings into some kind of pseudo-images, where basically these are fake images created by the embedding to try to then have a vision transformer instead. We then have here a vision transformer, which is trained on these fake images instead. And then out of that, we basically compute the image embeddings, and then we compute the similarity. The reason is we wanted to see what if we bring both of them into a similar domain first. One domain that basically both of them can be translated to, which is the vision domain. And then from that, we try to learn and see if that works. So here is, I'm not going to go through exactly how we created these images, but basically we just split the numbers into 3 different channels, like the first third is red, the second third is green, the third is blue, and then we just basically put them on a square image, and resized it and all of that. And then we scaled it, of course. And this is an example, an actual output of an example image. And this is how one of these fake pseudo images would look like. Of course, this has no meaning to us humans whatsoever. Like, I would never have thought that this is a car engine or something like that. This is just for the machine learning algorithm to try to learn meaningful patterns from it. And then we come to the experiment itself. So now we tested our method to see how good this would be. And we actually did this for a small reproducible simple experiment. We only trained on Clotho, not the other training sets. However, for the TK's challenge, I did use also the audio caps dataset to try to increase the data points on that. And we also tried to do some data augmentation too. So we used for the small experiment just 20 epochs and also a proxy image size of 224 by 224. And the results were very underwhelming. So the baseline system had 75% and our vision proxy had 71%. As you can see, from text to audio, which is what we care about. We don't care right now about audio to text, but yeah. And we also applied it to a DK's challenge with a lot more data, like I said. And the best configuration I got was still underperforming the baseline system. I mean, this is bad news, I guess. We don't have any good news in this thesis, but this is all normal. I mean, this is just also to present how this would look like and how your, thesis might be too. But I just also wanted to emphasize that even if your results were not that good, it's still meaningful scientific literature, to at least say what works and what doesn't work, which is very interesting. But let's come to the discussion. So why do we think it might not have worked? Our main findings are that replacing a projection head with a vision proxy, so, creating these pseudo images, leads to underwhelming results and leads to a loss in retrieval accuracy. So possible information loss when converting from embedding to image, meaning when we have an embedding and we convert it to an image itself, we think that there is some kind of loss of information that is happening, and that's why there is a problem. So some possible future improvements could be more data and better images. So I read, actually, I'm not sure how true that is, but it is worth a try that apparently vision proxies are a lot better if you just have a lot more data. So they become just a lot better over time. So that is something worth trying out maybe in the future, that maybe if we actually increase on data and the time spent, like the epochs learning, then maybe we could actually have improved a lot. And yeah, with the better images, another idea is what if we actually try to generate an image based on, based on the text query and also based on the audio query, and then try to learn from there. That could be one possibility, but it just increases tremendously on the complexity of the model too. And yeah, thank you very much for listening to this. I hope you learned a lot, and I hope you also had a nice insight into how a bachelor thesis might be for you.